Today we're going to be continuing our discussion of rational expressions and functions, which again is the parent function y equals 1 over x. This is the type of graph we're going to be looking at. In our previous video, we discussed how to find the key features, the vertical and horizontal asymptotes, and any removable discontinuities that might happen in the graph. So if those skills are not fully comfortable with your understanding right now, you might want to go back to the previous video just to review maybe the practice problems of how to find a vertical and horizontal asymptote, which is going to be assumed as we go through the next lesson, which is physically graphing a rational function from an equation, and then we're going to look at how to do this from a table. So this is the next part of our lesson. Let's go ahead and jump into what this situation is going to look like, or the strategy to approach this situation. Maybe pause the video, just write down these steps. Here's what you're going to be doing. Step 1 and 2 come from our previous video. You will get your equation, you will need to factor and simplify it, and then you will need to make note of any asymptotes or removable discontinuities. This came from the first lesson, which is the previous video to this series. What we're going to also be doing today is finding the x and y intercepts. We will identify the domain and range, and then we will have enough information to take a coordinate plane and physically draw a rough sketch of what this rational function is going to look like. So let's go ahead and take an example right here. Maybe pause the video right now, set up that function, and then also set up a 10 by 10 coordinate plane so you have enough room to draw what you need to draw. So we're going to begin by factoring and then simplifying. And you're going to notice in the denominator we have a quadratic that we are able to factor, and that will allow us to cancel out the x plus 4s that you can see highlighted right here. And again, if this is something that you're not fully comfortable doing at this speed right now, you will need to go back and look at the previous video, which talks about in more depth how to simplify these types of problems. So this is now enough information to proceed with simplifying and identifying our asymptotes. So because in the denominator we have an x plus 2, right there, you are going to have a vertical asymptote at x equals negative 2, which is the opposite according to the zero product property of the x plus 2 binomial. So there's your vertical asymptote, x equals negative 2. You will then notice that this function is bottom heavy. The degree of the denominator is bigger than the degree of the numerator. And because things are bottom heavy, you know the horizontal asymptote will therefore have to be y equals 0. And then lastly, because we canceled out the x plus 4 through simplifying, then you are going to have a removable discontinuity, and it's always at the opposite number, at negative 4. X equals negative 4. So all of that detailing came from the previous lesson video. Go back and check that out if you need a more in-depth review. Next is what we will now additionally do to build a better image of our graph. We're going to find the x and the y intercepts. You're going to notice with the y-intercept, you would simply plug in an x value of 0 to your new function, which is right here, 1 over x plus 2, our simplified function. And when you plug in 0 to x, you will get 1 over 2. So that is your y-intercept. It is at 1/2. Now, notice with the x-intercept, however, where you will plug in a y value of 0. So you have to figure out what x is when there's a 0 on the other side and the x is in the denominator. So what you would need to do is multiply both sides by x plus 2 to cancel it out of the denominator, and then think to yourself, well, 0 times anything is 0. So the left side of the equation is going to become 0 when you multiply, and then the right side of the equation is only going to have the number 1 left over. And since 0 cannot equal 1, this is a no solution situation, meaning the x-intercept does not exist in this problem. And that tracks perfectly with the fact that you have a horizontal asymptote at y equals 0. And y equals 0 is just the x-axis. So if the x-axis is an asymptote, then you will never have an x-intercept because the graph can never touch an asymptote. If that doesn't make sense, then just understand you got a non-true statement. So that means there isn't an x-intercept since 0 does not equal positive 1. The last thing that we will do is now state the domain and range, and we will need to do that by just taking our vertical asymptote, which was -2, and that means x cannot be -2. We're going to take the removable discontinuity, meaning x cannot be -4, and then our horizontal asymptote is at y equals 0, so 0 cannot be in the range. And then lastly, you're going to notice that -1/2 that is there. That is not the y-intercept. That is the removable discontinuity. Because remember, and this is again from the previous video, you will need to figure out what is the y value of your removable discontinuity by plugging that number, in this case x equaling -4, plugging that back into the new function, which is right here, 1 over x plus 2, and you can see the -4 right there when you plug it in. And when you do that, you would get -1/2, which is the y value of your removable discontinuity. Again, the previous video goes into that with a little more depth, so go and check it out if that is something you need to do. Let's now make the rough sketch. So start by plotting your asymptotes. You have a vertical asymptote at x equals -2 right there, and a horizontal asymptote at y equals 0. So plot your asymptotes first. Then plot your removable discontinuity. You know it's going to be there. And what you can see highlighted in purple now is how you get this value. The x value of it was -4. You got that from the second step of this problem. And then the y value is -1/2 when you plug the removable discontinuity back into the simplified function. And then the last thing to do, plot your y-intercept, 0, 1/2, because you know that is a concrete point that you were able to get. We did that work right here. You know there is no x-intercept, so you can now make your rough sketch. You're not going to be able to touch the asymptotes, and you know it has to go through the y-intercept. It's got to get, it's got to go through the removable discontinuity, so this is what the graph is going to look like. And on the next slide, you can go ahead and practice this for yourself, so let's just hop over there. Pause the video, try to graph the entire thing by following the same steps, and in a moment I will show you the solution. Okay, here we go. So after simplifying, you are going to get a removable discontinuity at x equaling 5. You will then plug 5 back into the function in order... Oh, it looks like I made a little mistake in the work. Oh no. We can fix that on the spot. That would be 5 and then 1/7. So let me actually just edit that on the spot right here. Let's just edit that. I guess this works out so you can take a moment to look at the answer a little bit. Let's just get a 7 right there, 1/7, because you plug 5 back into that denominator, and 5 plus 2 is 7, so 1/7, and you would just estimate that location. Again, no x-intercept didn't exist. And let's just go ahead and move on to the last part of the lesson, doing this same skill. So you're going to hear a lot of the same information, but you're now going to be extracting it from a table. I'm going to show you one of these, and then you can practice one and see how things go. The general idea is to understand your domain and range can always be determined from a table by looking at the values that are undefined. That's the key. Undefined locations are your asymptotes or your removable discontinuities. In order to figure this out, you're going to be given points that you are able to graph. They are defined, and then you'll kind of notice from doing this procedure where the asymptote is and where the removable discontinuity falls. So let's just go ahead and take a look at these. Basically, you're going to be given a table, you're going to be given a bunch of values, and you have to fill out the table and then graph everything to the best of your abilities. To help this along, I'm going to show you the function that we're working with, and on the practice problem, we're going to take the function away so that you can pick out the values that you can get just from the table. So the first thing to notice, we're going to start with our domain and range. The domain, it says in the table that -4 and +4 are x values that give you an undefined y value. That means you cannot include 4 and -4 in your domain. If you were to plug those numbers in, you would get a 0 in the denominator. And you can actually see that from the original function because it says x squared minus 16. 4 squared minus 16 is equal to 0. And you can't have a 0 in the denominator. So look for where it says undefined and you will know where your domain is going to begin. Next, in this case, just to support that point more, let's go ahead and factor the numerator and the denominator. So let's back that up. Both the numerator you can factor normally to get x plus 4 times x plus 3. And the denominator is a difference of squares, something from a previous chapter in Algebra 2 that I'm assuming you kind of remember. And when you factor the difference of squares, your answer will always be a pair of conjugates just by taking the square roots of your first and last term. So the square root of x squared is x. The square root of 16 is 4. So that's why you see the plus and minus 4 right there. And let me just get rid of those stray marks that I just put there. Okay. Next, notice that you were able to cancel out the x plus 4. That means you're going to have a removable discontinuity at negative 4. So this value was not an asymptote. That's representing a removable discontinuity. And you'll have a chance to practice this on the next slide where you're not going to have the graph. And what you're going to want to do to figure that out is plot all of the points that are defined so that you can see where your points are going to go. And then you can more easily figure out which is the asymptote and which one is the removable discontinuity. So we'll just keep moving with this problem to review the other key ideas, and let's just move things along. The removable discontinuity is at negative 4. You got to plug that back in to your simplified function in order to get the y value of the removable discontinuity. And by doing that, negative 4 plus 3 is negative 1 in the numerator, and in the denominator, negative 4 minus negative 4 is negative 8. And those two negative signs are going to cancel out and give you 1/8. So that is the value of the removable discontinuity. Since your denominator cannot be equal to 0, you know that a vertical asymptote is going to happen at x equaling 4, since positive 4 is the opposite of negative 4. You're going to have a horizontal asymptote at y equals 1, because remember, if the degree, so the exponent, and you can see the number 1 written right there, if the degrees are the same, then you just divide the leading coefficients of your expression to get your horizontal asymptote. And that's discussed more in the previous video, so jump back and check out the horizontal asymptote part if you need a better review of that situation. The x-intercept is at negative 3, and you can notice that the y value is 0, and on the x-intercept, the y value is always 0, so that's how you look for that point. And then likewise, the y-intercept is going to be at negative 0.75. This information gives you enough to establish your range. You cannot have y equaling 1, because that was your horizontal asymptote, and you cannot include the y value of your removable discontinuity, which was 1/8. So we have enough information to now graph the function, and it would look something like this. You have your asymptotes dotted in red. You have the removable discontinuity estimated there. Plot both your x and y intercepts, and then you can make a rough sketch. And all of these coordinate points could have also been plotted just to give you a better picture, which I would recommend you do on the next practice problem. So here's what you can now take a look at. So no functions being given, what I want you to do is pause the video and see how much of this table you can fill in, and then draw yourself a coordinate plane and see if you can plot all the points that you can see the value of and figure out, is negative 3 an asymptote or a removable discontinuity, or is it positive 3? And then see if you can fill out the whole table. So pause the video, see what you can do. This is the last practice problem that we're going to do today. And here is a rundown of the solution. So your domain cannot be positive or negative 3. You have your intercepts. Which one of those numbers is the vertical asymptote? Which one is the removable discontinuity? Or are they one and the same? Well, after plotting your x and y intercepts, you can see your situation right here. And then if you plotted more of the coordinate points in the graph, you will notice the vertical asymptote is going to be at x equals 3. I plotted the remaining points for you all over here, and you can see this part of the graph is looking like it's going to do that. This part would logically be doing that. So your vertical asymptote would therefore be at x equals 3, and that means you would have your removable discontinuity at x equaling -3. Now, at this point in the problem, if you made it this far, great job. What you aren't exactly able to figure out is the range, because you don't have enough information to do your horizontal asymptote tests using the degree procedure from the previous video. So it is perfectly fine to just estimate your horizontal asymptote. It looks like it's passing through the number 1. And you don't know enough information to establish the range. It's meant to be a rough sketch, so it's okay if you are getting the general picture without the horizontal asymptote and the range filled in. That brings a conclusion to this part of the video series. We have now talked about the key features of rational functions and how to find the vertical asymptote, the removable discontinuities, and any horizontal asymptotes. And we have now talked about how to physically graph these functions on a coordinate plane, which you will ultimately have to do on any assessments in the near future. Thank you for watching. Drop any comments and questions that you have, and I will see you next time.